Hello everybody, this is Dr. Bricker here with a video concerning chapter 15 and 16, so traveling waves and superposition of standing waves. So mostly about standing waves. Superposition means what happens when these waves add together, or maybe they subtract. Okay, so we do the first three sections of chapter 15. So the goal of chapter 15 is to learn the basic properties of traveling waves. Again, there's a lot of material in chapter 15, but we are just going to cover the first three sections. So traveling waves, and we'll talk a little bit about sound waves as well. More about this picture in just a moment. So the wave model describes the basic properties of waves and emphasizes the aspects of wave behavior common to all waves. And we'll see there's going to be two different kinds of waves mentioned. Transverse and longitudinal. We will be focusing on transverse waves. So a traveling wave is an organized disturbance that travels with a well-defined wave speed. So it's a nice uniform wave propagating through space, through a medium, really, I should say. So mechanical waves are waves that involve motion of a substance through which they move. So the top picture here this is a mechanical wave. There needs to be an actual substance that it propagates through. So that what it's propagating through is called the medium. There are electromagnetic waves, which we don't talk about in this class. They don't need anything to propagate through, but mechanical waves do. So this picture, there might have been maybe a pebble dropped in the middle and the wave spreads out from the middle. So a disturbance in a wave that passes through a medium. A disturbance is a wave that passes through a medium. So what you're seeing is a disturbance. And what do you actually see? You see the leading edge of the wave. Okay, so more about that in just a moment as well. So waves that involve motion through a substance, and we always have to have a substance here. So the substance could be like a wave on a string, for example. So the string would be the substance. Or it could be a sound wave propagating through air, and air is a substance. So we always have to have some sort of substance. Okay, so it's created by a source. In this case, a pebble was dropped here, and the wave travels with the speed. So each of these peaks are traveling with a certain speed. So a wave does transfer energy, but the medium as a whole does not move. And we'll see how that works out. Part of the if you think about the liquid here, the water, the wave, mostly what we're considering is different particles going up and down as the wave passes through it. Maybe a better analogy would be if you have a string pulled tightly, you flick the string doesn't go anywhere, but the pulse travels through the string. Okay, good. Okay, so more about all this information in just a few minutes. Electromagnetic waves, if you have to take Physics 221, we'll talk about electromagnetic waves in Physics 221. Things like visible light, radio waves, microwaves, X-rays. They do not need a medium to propagate through. That's a relatively recent idea, in the last 150 years or so. Okay, very good. And also in Physics 221, matter waves. So sometimes particles with mass behave like particles, sometimes they behave like waves. So when it says matter waves, we're looking at the wave characteristics of things that have mass. Okay, so believe it or not, you have your own wavelength. So transverse and longitudinal. Most waves fall into those two different categories. Transverse waves is the disturbance is up and down. As you can see here, the person is moving the rope up and down, but the wave moves to the right, and that's a transverse wave. Okay, so the disturbance is perpendicular to the direction that the wave actually moves. And that's the sort of wave we'll talk about with waves on a string. That's the focus of our wave section. Longitudinal waves, on the other hand, the push or pull, as you can see here, is in the same direction as the wave, and it travels with a certain speed. So this would be like a sound wave moving in that direction. And if you want to, you can check out this Ace Ventura video. Let me click on it actually. It's relatively short. So if you know anything about a slinky, you might have seen.
I'll meet you at the bottom. There's still one more thing I must do before I go. It's incredible! It's gonna be some kind of a record! Everyone loves a Slinky! You gotta get a Slinky! Slinky, Slinky, go, Slinky, go! Oh, man! Can you believe it? It was right there! Can I do it one more time? Please forgive me, somebody.
Okay.
I'll meet you at the bottom. There's still one more thing I must do before...
Anyway, that was just a little video about a Slinky. I thought you might get a kick out of it. So that's, again, Slinky moves this way, back and forth. That's where the push or pull is. That's where the wave is actually moving in the same direction. Okay. So the two most important type of earthquake waves are S waves, which is the transverse wave, and P waves, which is the longitudinal wave. So the passage of P wave extends and compresses the ground, and the motion is parallel to the direction. So again, P waves are longitudinal waves. So passage of a P wave expands and compresses the ground this direction, parallel to the direction that the wave is moving. So that's a longitudinal wave. The disturbances in this picture, left and right, that's the way that the wave is moving. P waves move faster, but S waves are more destructive. So S waves, the disturbance is up and down, but the wave moves this way. P waves actually move faster, but they're not as destructive. As you can imagine, if you have a house here, it's the up and down motion that is more destructive. Okay, so both kind of waves are associated with earthquakes. So here's a wave on a string. A transverse wave pulse traveling along a stretched string is shown here. So the string's not going anywhere, so the medium's not going anywhere, but different points of the string are moving up and down. So here's a blow-up picture of this spot here. So the string actually moves up because there's a net force up. There's tension this direction, tension that direction. You could look at the X and Y components. So what actually makes this part of the string move up is that there's a net force up. We can take a look here. After the peak is actually passed, the curvature of the string leads to a net force that pulls the string down. So if it's pulled down, accelerating down, there has to be a net force down. So although there's tension here and tension here, because of the shape of the string, this point moves back down. So as the pulse travels through the string, a point on the string goes up, and then it comes back down, but it doesn't actually go anywhere. The wave passes through it. So for it to move up and move down, there had to be forces on it. Okay, and that's the kind of wave motion we'll focus on in this class. Okay, so the curvature of the string due to the wave leads to a net force that pulls small segments of the string either up and down, and this continues on then. Okay. So each point in the string moves perpendicular to the wave motion, and again, that's what a transverse wave is. So you flick the string, that causes an external force, and then once created, the pulse just travels through because of the shape of the string. Okay, good. So you can transfer your information from one end of the string to the other by doing this. Sound waves are, on the other hand, longitudinal waves. So when a loudspeaker cone moves forward, it compresses the air in front of it. So here's the cone moving forward. The compression, that's what the actual disturbance is, and then the sound wave travels in the same direction as the compression. So a sound wave is longitudinal. I'm just mentioning it here. We're not going to focus on sound waves, though. Okay, so the motion of the sound wave is really determined by the medium it's passing through, the density of the substance here, the temperature, things like that. For a wave traveling on a string, it also depends on the medium, and really it depends on the linear mass density of the string. So thicker strings have a higher linear mass density. So this symbol is mu, mass per length. So linear mass density, so this would be like kilograms per meter. So the thicker the string is, the harder it is for the wave to travel through it. The slower it will actually travel. It also depends on how much tension the string has on it too. Okay, so the speed of a wave traveling on a string is equal to the square root of the tension divided by the mass per length. I usually sometimes will write it like this just to distinguish it between T for period. So this is force of tension divided by mass per length. Okay, and mu mass per length. Sometimes in problems the mass and the length will be given to you, so you have to calculate mu. Sometimes it's just quoted like this is the mass per length, and then it's just given to you. Okay, so let's take a look at this question. For a wave pulse on a string to travel twice as fast, the tension must be. Okay, so we can't just guess. We'll have to look at the formula and figure this out. So the speed is the tension, so I'm calling it force of tension, divided by mass per length. So if you want the speed to be twice as much, because it's proportional to the square root of the tension, you'd have to make the tension 4 times as big, and then the speed would be twice as big. So maybe if you want to look at it like this, what would the speed be if you made the tension 4 times as big? And then the factor of 2 would come out in front. That's just another way of looking at it. Okay, so it's twice as big as it was before. Maybe I should call this one V prime, just to distinguish it. So V prime is twice as big as the old V, because this is the old V. Okay, so don't forget about the square root relationship. Definitely if the tension's greater, the speed's going to be greater, but we have a square root of the tension involved. So increased by a factor of 4. And then this is similar to problem 1 from chapter 15 on homework 9. Here's another example we can take a look at. All spiders are very sensitive to vibrations. An orb spider will sit at the center of its large circular web and monitor radial threads for vibrations created when insects land. So the spider's sitting there, an insect lands, and there's a pulse on the web. Assume that the threads are made of silk with a linear density. Okay, this is mu here. 1 times 10 to the minus 5th kilograms per meter. And a tension, all right, good, there's the tension given to us in the problem. Both typical numbers. If an insect lands in the web 30 centimeters from the spider, how long does it take the spider to find out? So if we can calculate how fast this pulse is moving, we know the distance away, 30 centimeters, we should be able to calculate then how long it takes. Okay, let's take a look at this in a little more detail. So the speed, this is a new equation that we have just from today. Tension divided by mass per length, SI units, good. So this pulse is actually traveling at 200 meters per second. And then we could use stuff we learned in the first week of the semester. The speed is the distance divided by the time, so then the time is the distance divided by the speed, and you can see the units here. This comes out to be 1.5, if you put it in your calculator, times 10 to the minus 3rd seconds, or 1.5 milliseconds. So really quickly. Okay? So they might feel it before they actually would hear it. Okay, good. So let's just see the last section here. Graphical and mathematical description of waves. And I'll have to draw a picture for this one. So if you have a wave, I'll just draw like what you might have seen before with waves. Something like this. The distance from peak to peak is called the wavelength. So peak to peak, the time for it to complete one oscillation is called the wavelength. So lambda is the wavelength. How long does it take the peak to go from here to here? Well, remember what the period is. That's the time for one oscillation. So the wave speed is the distance that it travels, which is the wavelength. That's this distance here, the wavelength, divided by the amount of time. And that's the wave speed. That's where this is coming from. You have got to really think about this picture here. The distance it travels, lambda, that's the wavelength, divided by the amount of time, that's the period. Now, if you want to write it in terms of the frequency, you can do that as well, because the frequency is 1 over the period. Okay, or I'll just write it like this: wavelength times time. So lambda is the symbol for wavelength, measured in meters. Whoops, this is actually divided by the period. Okay, good. Excellent. So we've got one formula, square root of the tension divided by mass per length. We also have this formula, wavelength divided by the period. Those have to actually be equal to each other, and that we could use that for some problems. Let me include it over here. So the speed, tension divided by a mass per length, but that's also equal to the wavelength divided by the period. Okay, so that's a useful relationship we can use. Okay, so really that's the bit about chapter 15. This was the big takeaway from chapter 15. The speed is the tension divided by mass per length, the square root of that, and that's also equal to the wavelength time divided by the period. So we'll use that relationship in chapter 16. Just don't forget what mu is also. Mass per length. Okay, good. One thing about chapter 15 and 16, this is the standing wave chapter. It's only good for standing wave problems. So if you read through a problem that's talking about standing waves, we only have a certain amount of equations we can use for that. So they're very specific. So on your formula sheet, you should definitely have this relationship here. Have an idea what wavelength and period mean, maybe this picture here, and then also the last one we have there, the linear mass density, mass divided by length. Then we go into chapter 16, superposition and standing waves. So this just means what happens when waves pass through each other. They add together, they subtract, that sort of thing. So again, superposition just means the adding and subtracting of waves as they pass through each other. Okay? Something called interference. Sometimes constructive, they add together. Sometimes destructive when they annihilate each other. Okay, so this is a didgeridoo here. This is a wave in a tube. You'll see that this is in this chapter, but we're going to be focusing on waves on strings. Okay. So when two water waves meet, the motion of the water is a sum or superposition. So that just means you're adding them together. And sometimes they interfere constructively, sometimes destructively. And what you can get with standing waves on a string is a picture that looks like this. So on these low spots, the waves are actually killing each other off. And on the high spots, they're adding together. Let me change the color here. So here, they're killing each other off. These are called the nodes, actually. The low spots. And then here, they're actually adding together. These are called the antinodes. Antinodes. Okay, and we'll see how that works out in just a few minutes. That's just a little bit of definition of these things. So this wave has 3 antinodes. 1, 2, 3. So this would be a mode 3 wave. We have waves that go all the way from 1 up to infinity, really. This is just mode 3. Okay, the third harmonic, in other words. Okay, good. So we'll get into more detail with this. So here's the principle of superposition. If you had pitching machines, you've got this machine over here, A, this machine B. Now, if you threw 2 baseballs and they hit at the same spot, they don't pass through each other. The ball coming from machine A would deflect over to Alan. The ball coming from pitching machine B would deflect over to Bill. And they don't pass through each other. Waves, on the other hand, can pass through each other. So here's a loudspeaker. Both observers would hear undistorted sound despite the waves crossing through, so they could actually pass through each other. So Alan would hear the sound from speaker A and from speaker B, even though at this point the waves travel through each other. And then, of course, Bill would hear speaker B and speaker A as well. Okay, so that's kind of a neat thing with sound waves. So when 2 or more waves are simultaneously present at a single point in space, the displacement of the medium at that point is the sum of the individual waves. So here's wave 1 and wave 2, wave 1 moving to the right, wave 2 moving to the left. When they overlap here, you can see that they actually add together. So the amplitude here is the amplitude of 1 plus 2, and then they pass through each other and they continue on their merry way. So again, that's a neat property of waves. So you can kind of already get an idea here. Here's two waves adding together. How did we get this picture that we saw previously? You send several waves down, and if the frequency is right, you can get them to add together and subtract at certain spots. Okay, more about that in just a minute. Here are a couple of waves. The one on the left is moving at 1 meter per second. The one on the right is moving at 1 meter per second towards each other. Here they're about to interact with each other, and we can see what happens when they actually do on the next slide. Here's after 2 seconds. The one on the right has moved a little further to the left. The one on the left moved to the right. And here's what happens when they actually interact. This is the peak here. We're adding the triangle wave plus the rectangular wave and get this. So the shape would be this shape. And they start to pass through each other at 3 seconds, still adding together point by point. And then afterwards they just pass through each other. So while they were interacting with each other, they were both above the x-axis here, so they actually added together. They are both positive waves. Okay, here's one that is above on the left. Here's one that's below. What happens when they pass through each other? This is called destructive interference when this happens. Here you can see when they're actually lined up with each other. The one that's above the x-axis, here's the one that's below. So you add them together point by point. This is positive, this is negative. They add up to nothing. So they pass through each other and you don't see a wave. And then once they continue on, the waves actually reemerge. Okay, so here again you have nothing going on because they killed each other off. And here they are passing through each other. Okay, so we can build standing waves with this idea. And again, just like this picture here. So change the color again. So waves that are trapped and cannot travel in either direction are called standing waves. So this wave is just locked here between here and here. So it's a string. The string is oscillating up and down. And if you can get the frequency exactly right, you can get this picture to appear. So individual points on the string oscillate up and down, but the individual points, the string's not going anywhere, but the impulse is traveling down the wave. So pretend nothing's on here. You start this off. You send a pulse this way. When it gets down to the end, it turns upside down and heads back. And then you flick it again. So the one that was upside down, moving this way, gets to the end, turns back the other direction. And if this machine is flicking it at the exact right time, that wave can add together. Now pretend this one is traveling to the left. So again, we're starting from scratch. You flick it one time, a wave pulse travels to the right, gets down to this the right side here, turns upside down, starts heading back. When this reflected wave meets with another wave here, that's where they actually can kill each other off, and you get the nodes. So you have to have this just right. Flick it, send pulse after pulse down. They hit the end here, turn back upside down, and in some points they add together, some points they subtract. You have to have it set up perfectly, and you'll get a picture that looks like this depending on the frequency. Now, since we're not having any more in-person labs, you're not going to be able to see this, but we actually do this lab and we have this set up. We have an oscillator, and you can produce these waves. And it depends on the mass per length. It depends on the tension, that sort of thing. So we can control how many waves you see here by looking at the actual tension in the string. Okay. So I got a little bit ahead of myself, but that's okay. We'll talk about this in a little bit more detail. As two sine waves of equal length and amplitude travel in opposite directions along a string, The superposition occurs when they actually interact with each other. Going back to this example, this oscillator here, if it keeps going up and down, sending pulses out, the pulses flip back upside down and go the other direction. That's this one here. Get back to the oscillator again, turn back the other way. So this oscillator is producing several different waves at a certain frequency. Here it's just two waves coming from different directions. The oscillator one, it's just one oscillator making a whole bunch of waves. Okay, in a standing wave pattern, there are some points that never move, and these are called the nodes. These are the low spots again, and they're a wavelength divided by 2 apart. And the antinodes are halfway between the nodes, and that's where the amplitudes is the greatest. Okay, those are just some definitions. There's always one more node than antinode for a standing wave. So the wavelength of a standing wave is twice the distance between successive nodes or antinodes. Okay, so like pretend you have an actual wave here. Distance between here and here, that's a wavelength, right? Okay, so the distance between successive nodes then would be half of a wavelength. And you can see that from the picture there. Okay, so some definitions. So definitely have a picture, know what nodes are, know what antinodes are. So at the antinodes, the high spots again, the two waves have equal magnitude and the same side. So constructive interference happens at the antinodes, and destructive interference happens at the nodes. So this is sort of what happens. This is how you could actually build them. So you send a pulse down this direction. It hits a boundary, flips back upside down. And then just as this wave that's traveling to the left hits the area over here, you flick it again. So as this one's turning back right side up, you flick it again, and it adds together. And you can build these, build the waves like that. Okay, good. So with this situation that you see here, the before traveling this direction hits a different material. If the different material doesn't have as high of a mass per length, this wave is not reflected. But if it hits a boundary like a solid wall, it actually will be reflected upside down, and it will travel like this. Okay, so it's called a 180-degree phase shift when that happens. So this, what I drew here, would only happen if you interact with the medium that has a higher mass per length. So what I circled here is not happening in this picture. It would happen if it was like this, thinner to thicker rope. Then you would have that situation. Or if it's tied to a wall, you'd have that situation as well. And you can see that in the picture here. Okay, very good. So standing waves can be created by a string with two boundaries where a reflection occurs. So in this picture, you're just grabbing the middle and you're setting pulses left and right. They're hitting the edge and then flipping back around and coming this direction. You don't have to have that situation. You could have an oscillator on one end moving up and down and creating waves that way. So this one, you flick it in the middle, waves head in each direction, hit the boundary, and then come back, flipped upside down. And you can see what happens if the frequency is right. You can keep flicking this, keep sending waves down. If you have a certain frequency, you can set up standing waves. And they all live on the string in between the edges there. Okay, good. So my description, I've kind of already gone through my description part here. So a couple of conditions have to be met. At the edges, they are always nodes. So this is a node, and this is a node. And then the standing wave resides between these endpoints, and the length of this is just called L. That's not necessarily the wavelength. That's just the length of the string. You could have several different wavelengths on living on this string, as you saw earlier. We had a mode 3 earlier. And again, you could have all these different situations here. So this is the fundamental frequency, mode 1. Here's mode 2. Here's mode 3. Up to whatever, however many you want to have. Okay? So another way of thinking about the mode is, how many antinodes do you have? That's what the mode is, how many antinodes. So the wavelength, here's a formula for the wavelength, 2L divided by M. So in the first picture here, mode 1, this is actually half of a wavelength. Now if you put in 1 for M, you get the wavelength is 2L. So what you're seeing there is actually half of a wavelength. This distance from here to here is actually a wavelength if it's mode 2. So put in 2 for M and you'll see that the wavelength is actually equal to L. So this is the only case where the wavelength is actually equal to L. All the other ones you have to add it. Okay, so that's a good formula for the wavelength. That still works with what we did in chapter 15 as well. So we'll see more about that in just a minute as too. Okay, so this is what we saw before. The frequency, I guess we started like this actually. The speed is the wavelength times the frequency. So if you solve for the frequency, you'd have the speed divided by the wavelength. This is starting off with that step here. That's how the frequency and the wavelength are related to each other in terms of the speed. But now we can put in this new bit that the wavelength is 2L over M. So there's multiple frequencies. There's the fundamental frequency. So when M is equal to 1, that's called the fundamental frequency. And then the higher harmonics are just multiples of that. So when M is equal to 2, that's called the second harmonic. That's twice as big as the fundamental frequency. When M is equal to 3, that's the third harmonic. That's 3 times as much as the fundamental frequency. Okay, so if it's a wave on a string, like a guitar string, it's oscillating with a certain frequency. The string is oscillating with a certain frequency. It's in contact with the air is oscillating with a certain frequency, the air is oscillating, that sound wave travels to your ear, and then your ear oscillates with that same frequency. So the frequency of the standing wave on a guitar string is what you eventually hear, because the air is oscillating with the same frequency, your eardrum is oscillating with the same frequency, and that's how you hear things. So guitar strings have different lengths, different mass per length, different tension, so they can have different frequencies that way. And here are the different pictures of what these things might look like. Okay, good. And too bad we're not actually doing the lab in person. We could make these waves in the lab. It's almost a miracle when you see it. Okay, so there's the fundamental frequency. That's when M is equal to 1. Okay, and then the higher harmonics are just multiples of the fundamental frequency. So if you know the fundamental frequency, the second harmonic is twice as big as that. The third harmonic is 3 times as big as the fundamental, etc. Okay, so before we do that, let me kind of put all this together for us. So the speed is the tension divided by the mass per length. Okay, this is also equal to the frequency times the wavelength, but then the wavelength is 2L over M. Okay, so this is kind of putting everything together. So all these different parts work with each other. So, this is equal to this, and that's equal to this. So you can set all the different parts equal to each other. So what do I mean by that? Something like this. The square root of the tension divided by the mass per length is equal to 2L, F over M. Okay, so be careful. This M is not the mass. This is the mode. So you have to be careful with that. We have m for mode. This is the mass per length here. So, you've got to really pay attention to what different things mean here. Okay, so on your formula sheet, don't just have m and m. You won't remember which one is which. Have a nice detailed look at this. Okay, very good. Here's a nice example we can take a look at. A 2.5 meter long string vibrates as a 100 hertz standing wave with nodes at 1 meter and 1.5 meters. Okay, so the length of the string is 2.5, and we know we have nodes at 1 meter and 1.5 meter. Okay, good. The frequency is 100 hertz. Which harmonic is this? What is the string's fundamental frequency? And what is the speed of the traveling wave on the string? Okay, good. So we're equipped with these formulas that we had earlier. Hopefully you've written them down somewhere. You have to keep in mind what the picture looks like. So if the string is 2.5 meters long and we've got nodes at 1 and 1.5 meters, they're half a meter apart. All the nodes are spaced a half a meter apart. So it must look like this. 1, 2, 3, 4, 5 antinodes. So this is mode 5. The fifth harmonic, in other words. Okay, so which harmonic is it? Just from the picture, it's got to be the fifth harmonic. And then we want to figure out what is the fundamental frequency. Okay, let's actually take a look at this, put it all together. Here's what we know. We've already found the mode. We want to figure out the fundamental frequency. So F1 is the fundamental frequency. And then we want to figure out the wave speed. Now the wave speed is whatever it is. The wave speed, remember the equation, tension divided by mass per length. It doesn't matter what the mode is. The speed just depends on the tension and the mass per length. So if this were mode 1, mode 5, mode 10, mode 3, it doesn't matter. The speed is going to be the same. What changes is the frequency and the wavelength. Okay. I think this is a synopsis of what I've just said. Okay, very good. So the fundamental frequency, here's really the formula. We had Fm is equal to m times the fundamental frequency. So right now we know this is mode 5, so we know that the fifth harmonic they're telling us is 100. They're telling us this in the problem. So we've got to figure out the fundamental frequency then. We figured out it was the fifth harmonic, and they told us the frequency. So the fifth harmonic frequency was 100 hertz. The fundamental then is going to have to be 1/5 of that, or 20 hertz. Okay, good. I don't see it actually. Oh, here it is solved. 20 hertz. All right, very good. So we know the fundamental frequency. Now we need to figure out the speed. Well, we can do that in a couple of different ways. Now that we know the fundamental frequency, we can figure out the fundamental wavelength. So the wavelength, 2L over m. So when m is equal to 1, this wavelength turns out to be 2L. That's what's happening here. That's where that equation's coming from. Okay, so the wavelength is 5 meters, the fundamental wavelength. The fundamental frequency was 20 hertz. So the speed is equal to the wavelength times the frequency, so 20 times 5. So we got the wave speed from the fundamental wavelength, fundamental frequency. You could have used the fifth harmonic frequency and the fifth harmonic wavelength if you wanted to. You would still get the same wave speed. Okay, good. Oh, and that's actually what's being done here. So 100 hertz was given. You could get the fundamental, the fifth harmonic wavelength actually by 2L. So 2 times 2.5 divided by 5. And you would see that this turns out to be 1 meter. That's where they're getting this number from. Regardless of which way you do it, the speed is going to be the same. The speed is just the square root of the tension divided by the mass per length. The tension's not changing, it's the same string, so same mass per length. Okay, very good. So the fundamental frequency can be written in terms of the tension. This is what I tried to do earlier. This is the fundamental frequency. Okay. Very good. And then that's just the fundamental frequency. You can do the same thing that we did before with the mode. Let me go back to this. And I have it here. Okay, this equation. This is maybe a little more general. No, so if you want to make it look the same, just solve for the frequency in this formula. And then you'll have it in terms of the mode. Okay, whereas this formula, this is just for the fundamental frequency. Okay, you're just missing an M in this equation. Okay. Okay, so when you pluck a bow or a string of a guitar or whatever you're trying to play, initially you excite a wide range of frequencies. However, the resonance sees to it that only the frequencies to persist are those of possible standing waves. Okay, so with the guitar string, you can make it longer or shorter by putting your finger on the string. So when you do that, you actually make the length of the string less, and then you can make the frequency higher if you do that. Now a guitar has 6 different strings from thicker to thinner. So thicker strings have a lower frequency, thinner strings have a higher frequency. And then when you're tuning a guitar, you change the tension. So you can change all these different properties. You change the length by actually putting your finger on the string, and then just part of it is oscillating. Thicker strings versus thinner strings, that's where the mass per length comes into play. And then the tension here, you can change that by adjusting the pegs on the guitar. So you can make the tension greater or less. So really the formula that you see here for the fundamental frequency is, maybe that's where you should start if you want to learn to play the guitar. Okay. And then here's a couple of questions that are addressed in the homework video. Okay, so really that's the part of chapter 15 and 16 that I wanted to talk about. Just some general properties of waves, and then specifically standing waves, and then now we see how to calculate these different things. Okay, so go back through this video, read through the chapter, and put these equations together in a way that you understand. Make sure you know the difference between mass and mode, and then you have equations for standing waves. And it's very specific. If you see a standing wave question on the test, you have very specific formulas that you can use to solve that. Okay, talk to you soon. Bye-bye.